Okay, hello everyone. We continue our course, and in last week we've discussed the algorithm and the how to describe the algorithm, like the three stage from our language, the human language, to the pseudocode, like the fake code is partly of the code and contains some mainly contain English and finding to the code that computer or the machine will recognize. That is three stage about the algorithm. And then we'll begin the talk about the how to analysis of the algorithm. How to analysis of the algorithm. So the uh, analysis of algorithm is the theoretical study of the computer program performance and resource usage. So we care about the performance, mainly in the programming. So what are the details we care about the performance? So we want to know two things. First is we call it the time complexity. Time complexity is about the time. We want to make the make things fast. So why is that the time is important? Because sometimes you need your program for do some real time operations. So the time is important at that time. And another thing is about the space. We call it space complexity. And in our textbook and in our class, we'll mainly talk about the time complexity because the methods or the way to analyze the space is much similar to the time, and it's not as important as time, because if you found the data take too much space, you can just cut it into small pieces to handle it, and that's the simplest way to solve the space problem. But you cannot do the same thing to the time. You cannot cut the time. So we mainly talk about the time complexity here in our class and also in our textbooks. Okay. We're going to start out with a very simple question or simple problem, that is sorting. You may have already tried to solve this kind of sorting problem in your previous C class. Okay, so it's one of the oldest problem that has been studied in algorithm and in programming. So it's sorting. So what is sorting for? Suppose we have the input. It's a sequence of A1, A2 until AN, and all of them are numbers. And the output is a permutation. Oh, the series is answering again. I need to shut down the. It's weird. If I didn't close the cover of the iPad, the Siri is always answering me. Okay, let's continue. We have this kind of input sequence, and the output is a permutation. Permutations means rearrangement. Means you put the A1, A2 to AN in different orders, and the permutation is A1 prime. This should be prime, called prime, and such that the output should be A1 prime less or equal to A2 prime and less equal to A3 prime until the AN prime. So we'll make it the increasing sorting. You can also do the other way from the largest to the smallest. Doesn't matter. Okay, that's the purpose of sorting. So we rearrangement the input, and put them in order to increasing inside. So that's our purpose. So how do we solve the problem, the sorting problem? So you may learn this, I guess, like called bubbling sorting in your programming language C course, bubbling program. You each time find the smallest or the largest number in the sequence and to pull it out. That's bubbling. And here we try to another way. We call it the insertion sort. I don't know whether you have learned this in your C course, language C course. So the idea is pretty similar to the bubbling sort. So suppose we have the input, we name it as A. It's an array, basically it's an array, and the total number is m, and the index is start from 1, not from 0, from 1 to n. Okay, so then what the insertion sort will do. Suppose this is the all the numbers of the array, or you can call it array, and in some point we try to pull the value out, and we call it a key. Okay, that may be in the position of J. Okay, we can call it position J, and the key point is here is before the key, like this part. It's already sorted. It's already from the smallest one to the largest one, and in order. It's already sorted, increasingly sorted. So in this step of this inserting sort, what I'm going to do is try to add one length. Add 1 to the length of this part, sorted part. And how do I do that? I compare the key. I compare the number of key to the previous one until find a place. Okay, until find a place, and I will put the key there. So that's a operation of insert. So this kind of method is called insertion sort. So you try to find the right place for the key, and the arrow is in the wrong direction, should be this, and copy others to the behind. Okay, in order to find an empty place to insert the number key to the right place. Okay, to the right place. That is the insertion sort. So example, we have 6 numbers, the 8, 2, 4, 9, 3, 6. Then what's the insertion sorting would be like? So at the very beginning, actually we start from the number 2. The number 1 is, we think right now it's already sorted. This is sorted part. So we take the A2, that is number 2. Right now the A2 is the key. So we compare the key to the previous part, and we know we should put the number 2 to here, right? So we copy the 2 to here. Right now the sequence will become to 2, 8, 4, 9, 3, 6. Okay, now this part becomes the sorted part, and the next one, number 4, becomes the key. And we just repeat the process again and again. Try to compare the key to the already sorted part. That's the part before the key. And try to find the place for the key. So we found the 4 should be there. Then the sequence should be 2, 4, 8, 9, 3, 6. Okay. So next is the number 9. Number 9, you found it's good. You don't need to copy anything. You don't need to move. It's just here. But actually the programming was still running, right? It's still comparing. So I will write down again. So the sequence would be 2, 4, 8, 9, 3, 6 again. And right now the key is 3. Then you found 3 should be here between 2 and 4. And the sequence is 2, 3, 4, 8, 9, 6. Okay, and the last one is a 6. You will find it's here. The sequence should be 2, 3, 4, 6, 8, 9. And it's done. Okay, it's done. So this is a process of the insertion sort. The key point is try to pull out the value, pull out a value at a certain time equal to key, and compare a key to the previous part. And the previous part we think it's already sorted, and we're trying to find the right place for the key right now, and try to insert it. That is the insertion sort. Okay, that is the insertion sort. And we will talk about the time of this insertion algorithm. How to calculate the time of the insertion sort problem. And before that, try to do an exercise. That is to try to describe this insertion sort algorithm in the pseudocode. Do you still remember the pseudocode? I talked in last week. You can call it fake code if you directly translate the Chinese into English. Should be the fake code. That means part of it is the code, like this. You need to use the loop, so you can still try to write down the for loop or while loop. But part of it is our human language. Of course, mainly used in English. Here, you can still write your native language or Chinese. That doesn't affect. So, for example, how many layers of loop do we need in this insertion sort? How many layers? Try to think about it. It's 2 layers, right? Because we need to the out layer should be the place of the key, right? you should move the very beginning to the end. So the outer layer should be the we call it J, okay? Should be the J. So the J should be from some students think it will start with 1. Actually, the first one you don't need to consider, like the example, the 8. You don't need to consider 8 before it, because nothing before it. So actually we start from what? From 2. So J is from 2 to the end. That is our the outer layer of the loop, right? Then we need the inner side of the loop. What the inner side to do is we compare all the numbers before the key, right? We need to compare the key to the one previous, that is J minus 1 and J minus 2, until you find the right place for J. So we have an inner layer of loop. So it's totally 2 layers of loops. So I will left the other part for you for exercise. Try to describe this insertion sorting algorithm in pseudocode. Okay. So next thing is, how do we calculate the time of this kind of code? The time, we care about the time. We care about how to make things fast. So how to calculate the running time? So first you need to know it depends on a lot of things. To the sorting problem, first it depends on the input itself. What is the input itself? For example, it's sometimes the best case is the input is already sorted, right? That is, you are very lucky and the input is already sorted. Like the input is already the 1, 2, 3 is already increasing input, and the time of the algorithm would be very short or very fast. And on the other hand, sometimes you got a really bad input that is reversed. That means the largest is at the beginning, like the 8, 7, 6 until 1. It's totally reversed. So you need to compare compare all the numbers before it, and try to spend time to move the numbers. It takes a lot of time. So the running times depends on input itself, and it also depends on the size of the input. That means just now the example I've used is just the 6 elements, right? So how about the input n is become the 6 times of 10 to the 6. The time of this would be much longer than just the 6 element, right? So the running times depend on the size of the input. And another thing is we want to know the upper bound. Think about that. Why we need the upper bound? Because only the upper bound is a guarantee to the user, to ours. Guarantee, that is a promise, like promise. For example, if you say, this program I give to you, it won't run like more than a second, then you know it will finish at most 3 seconds. So you can do some real-time setting. The longest time we'll spend on this part would be 3 seconds. So that is a guarantee to you. Okay, So on the other hand, if we give the lower bound, that is like it's the for example, the lower bound would be you talk to others like the program where goes like at least for 3 seconds, at least. So is that give us any useful information about this program? At least 3 seconds. No, it doesn't give us any information because we don't know what exactly the total time we'll spend on this program. It's probably 3 minutes, right? And it's probably 3 years. So it won't give us any promise or any guarantee. So in the running time to analysis the algorithm, we want to know the upper bound. So that's what we want, and we don't want the lower bounds. Okay, because that's not a guarantee. So that's you need to know before we to really calculate or to analysis. That's about the upper bounds and lower bounds, and what we want is the upper bound. So what kinds of analysis are we do? So the first is we call it a worst case, and it's done usually. We usually take the worst case. So think about why we talk about worst case, and the worst case is actually the upper bound, right? The worst case. And we take a look at the definition of the worst case. It's the Tn means worst case means the maximum time on any input of size n. No matter the, for example, sorting, no matter is sorted or reverse sorted, we don't care. We need to know the any input. That is saying, if you give the worst case, we try to explain it in our language. It would be it always does something. Okay, always is the worst case, rather than just sometimes. So that is the worst case. So always means a guarantee or promise, right? So if it just happens sometimes, that won't be the guarantee. For example, like the salesman right now, and a salesperson trying to sell you a car, they actually always use the like the best case, not the worst case. For example, they talk about the oil consumption. If you buy a car, they will always talk about the oil consumption. So probably the advertisement will talk about this car is the oil will be just maybe 6.9 liters per 100 kilometers. So that number is actually sometimes happen when you really buy the car and you drive it for a time. You can take a look at the oil consumption. You will find it's probably 7 plus or even 8 plus liters per 100 kilometers. So the salesmen always trick you like that. So they always, or the advertisement will always show you the good case, not always. So that's not a good idea in software engineering. So in the programming, we should provide the guarantee, what's the situation would be always like, not just sometimes. Okay, that is the example. And the series is running again. Hold on. I will shut down this series. Okay, and the unit we use in China is the always use the meter, kilometer, and the liter. And in the US and in the Great Britain, they will use the inch. I don't know what's what the unit was used in your country. Okay, that's the worst case. That's we usually try to do. And another thing is the average case. That were used sometimes. Then what is the meaning of average time? Average time means the expected time over all inputs of size n. Expected time, do you still know about that? If you have learned the probability, you should know the expected time. Some students may think that is a kind of average, like T1 plus T2 to Tn, then divided by n. That is the average time of t. You cannot call it wrong, okay? It's actually right, but it's not quite enough. So the expected time should be the time of every input and the times the probabilities. So if we have the all the possible situation x1, x2 until the xn, and the probability of each is p1, p2, and pn. The expected should be the xi times pi, and we plus it from the I to from plus the I from 1 to m. That is expected in the probability. So the next question is like, how do we know about the probability? How do we know about the probability? So the expected time is the time of every input, and the times that means multiply. The times means multiply the probability. So how do we know about the probability? The real thing is we don't know about the probability. So if you need to calculate the average time or average case, we need to make assumption. Assumption what? Assumption of the statistic distribution. So if you have the statistics distribution, you know the probability, then you can calculate the expected. And usually, like, we will assume that all inputs are equally likely. That's why we call it uniform distribution. Or if you directly translate the Chinese, that should be average distribution. That means it will show up the probability of every possible number is equal, and the distribution would be like this. If it were show up from maybe from A to B, and the probability from A to B is the same. So every possible the probability of every number to show up is the same, is equally the same. So that's called it uniform distribution, or we call it the average distribution. So it's actually a little more complex than the worst case when you try to calculate it. So we just sometimes use it, not the usually, because the average is pretty hard to define average in different situations. So that's the first two, worst case and average case. And we have another one. It's a best case. Best case. Although the best may sound like a good word, but best case in the analysis of algorithm is, we call it the bogus. Do you know the word bogus? It means it's fake. It's not true. It's no good. For example, like the sorting problem, like you're really lucky. Like the input is already sorted, 1, 2, 3, 4. It's already sorted. Then you put it into the computer. That's the best case. But that will maybe never happen in the real life, right? The best case maybe never happen. So it's no good for us. It's not a guarantee. Like the example I mentioned you before. If you tell others your program we're running like at least 3 seconds, though, then you never know if it were going to run like for 3 years. So it's not guaranteed. So in the analysis of algorithm, we usually don't talk about the best case. Okay, just to bring up to let you know. We need a guarantee, so we need the worst case. We need a worst case. So next question would be, how do we calculate the worst time, worst case? We just try to use a very simple example that's in our textbook, section 2.4.1. If you have a textbook, you can take a look at the example. It's a pretty simple program, just 4 lines. First, you can read it quickly to say what is this short program for. So you say there's a for loop, right? And it will calculate the sum. That means you plus something together. So do you still remember this expression? Plus equal. That actually means the sum equals sum plus, right? The same thing. I times I times I. That actually is I cube. That is I times 3. Also, you can say it I cube. So this program is to actually calculates the I cube and to plus it together from when I from 1 to n. So this short program is to calculate this. Of course, it's just part of it. There's no like the before or the title. The whole part is in the textbook. I just show you this 4 line. Then how do we calculate the worst time of this part? How do we calculate the time? Okay, some students will just think about how about we plus all the time together, like figure out, try to what the time is for line 1 and the line 2, and what's time for line 3, and we plus them together. That should be the total time. Okay, let's try this way to see what will happen. Okay, the first line sum equals 0, then the computer does in a, we call it a constant time, so during a constant time, but the time is how long, we don't know. If we need to calculate, we might be make assumption like the equal spend some time, the symbol of equal spend some time, then the time might be we call it t0. Okay, so we take a look at the third line first. So how many times is this part span sum sum plus equal to I times I times I. So how many calculation does this line do? He actually calculate one time of the plus, right, and one time the equal symbol, and the 2 time of the times or multiply. But how long will take if we do the plus calculation, and how long it will take for the multiply calculation? We don't know, right? So probably need an assumption too. This part is T1, and this part is T2, this part is T3. Then totally would be T1 plus T2 and plus the 2 times T3. And totally how many times this part will execute, it will depend the loop, right? How many times? Likely to spend n plus 1 time, n plus 1. Okay, this part I less or equal to n, then this part will execute. So totally like spend the n plus 1 time. And also inside the for loop, how many times of this I plus plus will execute? It will spend like the nth time, right? But each time, how many of each time will spend, where it's spent, you don't know. Probably you can call it T4. So if you do the calculation, the time calculation like this way, yes, there's never end about this. Because of what? Like we had the assumption we made here, like the T1, T0, T1, T2, T3, etc., T4, etc. That is what? That is depend on computer. That means it's can have a lot difference between different computer. Like we say, if you use a supercomputer, like from the Microsoft or from the Google supercomputer, they may have provide to you. Or how about if you use a laptop, it will much slower to do the same thing, to calculate a plus or times or multiply, and even you can use a watch, right? Sometimes nowadays the watch can do calculation, and it will much slower. So if you try to calculate this way, like try to figure out every details, that is nearly impossible. So it depends on computer, and we need to analyze the time, and how to analyze the time without talking about the hardware. So we need something more with some tools or some other big ideas to ignore the effect of hardware. So we need the other big ideas. And the big idea is we called the asymptotic analysis. Asymptotic analysis. So this word asymptotic, some students may don't know about this word, because the most Chinese students don't know this word, and since the English is the both a foreign language for us, so I assume many of students don't know this asymptotic. So if you don't know an English word, since you have the bilingual background, you can check the same word in Chinese, actually, like the algorithm I mentioned in the first class to you is understand much easier the word algorithm in Chinese than in English. So asymptotic, that in Chinese means the 渐进. So can you recognize these two characters? 渐, what's 渐 mean? If you make it to a word, it means 逐渐, that's gradually. And this word is you should know it's about near or far. The operated word is far, so it's near, or you can make it to a word 接近, that means approach. So asymptotic means gradually approach the basic meaning of it. And in the algorithm analysis, that means we ignore the machine dependent constant. Like last slide I mentioned to you, this assumption made like t1 t0 t1, like how many times if this code will take like I equals to 1. It's totally depend on the machine you use, right? Is it a supercomputer, or is it just a normal computer, or your laptop, or your iPad? It were all different. So the asymptotic, we ignore this part, okay? Ignore the machine dependent constant, okay? Then we look what? We look at the growth, okay, of Tn. We look at the growth of Tn as n approaches the infinity. So that's a big idea for the algorithm analysis, okay? If we calculate it by the detail, like the last slide, if we care about this exactly time was spent on each part, like I equal to 0, I equal to 1, I plus plus, how much time will this part take? You can never calculate a time, so we need a more big idea, more huge idea. That is the asymptotic analyze. We ignore these parts and turn to look at the growth of the Tn from the n to 1 to maybe 10 to 100 or 1000, then to the infinity. How the Tn will change as the n grows, okay? So that's the tool or the big idea of how we analyze the algorithm. So in order to understand the asymptotic, we need some notation to help us. Okay, some notation. That's, you can call it symbol, but it's more precisely when to use the notation. Okay, we take a break for 10 minutes. Like we continue